Yeah, so welcome. First, I'd like to thank all of the guys at Signify for inviting me here. They flew me over, which is really cool. Yeah, so thanks. And my talk is called "Oh, All the Things You'll Traverse." And it's kind of like, I'd like to introduce you to like this library called CATS. Some of you have probably heard of it. And especially there, we're going to talk about this thing called traverse, which is, in my opinion, one of the most productivity boosts I've ever had in my whole programming career. So yeah, my name is Luka Jacobowitz. A quick about me. I work at a software consultancy, but I don't consult. I only develop. It's called Codecentric in Düsseldorf. Where I also organize the Scala Düsseldorf and the Idris Düsseldorf meetups. So if you're ever in town in Düsseldorf, be sure to check it out or talk to me if you want to give a talk. We're always looking for new speakers, especially for Scala. Yeah, and I also maintain the CATS and CATS Effect, CATS MTL, and Outwatch libraries. Which are all a part of this cool ecosystem called Type Level. I don't know if you can read it with this microphone here, but yeah, we're trying to build like a really cool ecosystem of libraries that are all really easy to use, very simple, and very purely functional. And with that said, I'm really enthusiastic about functional programming in general, not just Scala, but especially in Scala, and I want to bring some of that enthusiasm over to all of you. So what we're going to talk about today is very basically, it's just four things. So we're going to talk about this concept called type classes. Some of you might have heard about them. We're going to talk about this thing called monoids, which sounds a bit weird, I guess, and functors, also a bit weird, and traversals. But what the goal of this talk is basically to tell you that, hey, these things, this sounds scary, this sounds like some really abstract math. I don't know, I probably need a PhD for this, but I'm going to try to convince you that these things are actually really simple and they're really well defined, and understanding them is not that difficult. Okay, without further ado, type classes. Who has heard of type classes? Can I get a quick hands up? Who has used type classes? That's still quite a lot. Okay, that's cool. So what type classes give us is this thing called ad hoc polymorphism. And it's quite a bit different from the standard subtype polymorphism that a lot of us are used to when we're doing Scala or other object-oriented programming languages, which is basically creating an interface or a trait in Scala, and then having instances implement these traits, right? So if you have like a trait called list, then you can implement it using an array, and you have an array list, or something very simple like that. And it's actually like the type class. The idea is very similar. You also have this interface, but instead of like implementing it at the definition site, you implement it after the fact, and that's why it's called ad hoc polymorphism, because you can define instances for these type class interfaces in an ad hoc way. So with that said, there's no like explicit language support in Scala. That might change in Scala 3.0 in Dadi. But we can get a very, very, very close and very like a very good feature by using implicits, and we'll see how that works. So this is a very, very small type class example, and it's for a type class called show. And the show type class is really, it's not super complex. It's just a very simple example. We have this thing called show, of course, the trait. And the way we do it in Scala is we just define a trait with a single type parameter. And the type parameter is basically going to be the type which the interface is based on, right? So, and we also use this add type class annotation, which comes from from a small library called Simulacrum, and all it does is basically making the whole thing more first class. So you don't need to use Simulacrum, but it makes it easier to find things like infix syntax and these things. So this show type class takes a type parameter t, and it has a single method called show, which takes a value of type t and then returns a string. So it's basically like the type class version of the toString interface, which is not really an interface in Java because in Scala because every object implements toString because it is defined on the Java object. And what we can do then is we can define these instances, as I called earlier, and we don't define them like, we don't say, hey, string extends show. What we do instead is we define an implicit value of show for our type. And in this case, it's string and integer. So we define them after the fact. And that's why it's called ad hoc polymorphism. And that is like the main benefit of type class. And we'll see why that is cool in a bit. So we have this implicit val show string. And the only thing it does is define a new value of show. And then we just say, hey, because string is already a string, we just give it back. This is just the identity function. And with integer, we're just going to call toString. And the fact that this is just, the underscore is just a function is because, of course, in Scala 2.12, we can make use of the SAM types. And that means that every interface with a single abstract method can be just compiled to a function and vice versa. So this is how you define instances for type classes, right? So now we can use this type class, and that looks like this. So we have this method called empty of false, and it works only on, oh, I'm sorry. I don't know. Yeah, I don't know how to fix that. Sorry. Okay. Anyway, we have this method empty of false, and it has an abstract type t. But this method will only be able to be called if the t has an instance of the show type class in scope, right? So if we only have these two values right here, these two implicit values, we can only call this empty of false with string or integer as the type t. And then this double colon is called the context bound, and it basically desugars to an extra implicit value, right, an extra implicit parameter that says, hey, I need a value of type show of t here. And that's what it is. And so this t.show syntax right here, that is the only thing that Simulacrum does, right? So that's where it comes from. Okay, exactly. So right, so exactly as I said earlier, this Simulacrum basically allows you to call all of these types in an infix way. Otherwise, you would have to say, hey, implicitly give me the show instance, right? Give me this thing, and then call show, and then pass the value. So it would be a lot more boilerplate. And this way, with Simulacrum, we can just do it like this.
So basically, Simulacrum will transform the case of the type class into a list class.
No, not really. It will still have the shape, but it will also add an implicit class that you will have to import usually, unless you're in the same scope. And in that implicit class, it adds all of the syntax method in an infix way, right? So, but there's some other options. I don't want to go into like the details of Simulacrum because that's a whole nother talk probably. But this is the basic idea, right? So we constrain our types, our type parameters t, to a specific type class, and then we can use them in an abstract way. Right, so this was neat, I guess, but let's look at something a bit more useful. And this is what I call the monoid, or this is what math has called the monoid. This comes from like abstract algebra, and apparently they teach that in like 8th grade in Romania or something, but they don't teach it anywhere else. So, but it actually like the concept.
Watch out.
The concept of a monoid is actually really, really, really easy, and it only has two abstract methods that we have to define. And the first one is called empty, and it says, hey, I have to have this neutral element of type t, and the other one is just a combined function. So given an a and a b, both of type t, we return a new type of t. And well, if you think about it, there's a lot of different ways we could implement this for a lot of different types. For example, with integer, it's just, hey, of course, the empty value is 0, and the combining is just addition, right? And we could also do the same for, well, this is int again. And what we can see right here is actually that that we can use this this monoid structure to fold things, right? So this 0 and plus is what we saw right now. So yeah, it's a quick spoiler because I'm going to have to reveal all this. So we can do the same thing for string, right? Where the empty string is the empty element, and then we can concatenate strings. But we can also do this for things like sets, right? A set of something has an empty, right? That is an empty element, and then union is like the set combine element. And all of these functions are actually like a specialized version of this last function called sum, and it just takes an abstract type t with a context-bound monoid. So if you want to call this sum function down here, you'll have to call it with a type that has a monoid instance. And what we can do then is say, hey, if I have a list of t, I will always be able to fold that down into a single t using fold left and the monoid empty and combined types, right? So in essence, like aggregating a list is just exactly what monoid, like that's exactly where monoid fits in. So if you ever want to like aggregate a bunch of things, like a sequence of values, and you might actually be able to do that like just with a single monoid, and we'll see why these things are cool in a second. So right, and so you might wonder what the hell this is, this monoid t.empty, and that is actually another thing that is from Simulacrum, and that is also another thing that is really important, is that if you use type classes, you can define values or define functions that don't work on actual like instances, right? So right here we call a function where we don't actually have a value of type t, right? So and if you were to do the same thing with a simple Scala trait, right, with OOP and subtyping, you wouldn't be able to define this kind of method because empty is not a method on a value of type t, but is a method on the sum of type t's, right? So it's a function that works on the type instead of on single instances of the type, right? And that is the main difference between type classes and interfaces or traits, is that type classes, they work on the type level, right? So they define behavior for types, right? And that's exactly why we can use this empty. And yeah, just a quick to explain why this is cool, right? And of course we can use and define this for a lot of other types. But one thing that is really cool is implicit derivation, and that is like the coolest feature for me for type class. And this looks kind of big and stuff, but what we can do right here is say that, hey, I want to have a monoid for option, and this is of course defined in cats itself. And the only way to have a monoid for option is if the t inside of that option also has a monoid. And that means that, hey, I want to combine two monoids. Let's see if they're both sum. If there's a value, we should combine, right? We should combine right here. We should combine those values, and that pipe plus pipe is just a symbolic operator for the combine method that we saw a couple of slides earlier. So that is the exact same thing. That is just like the nicer looking thing. So that is monoidal combine. And what we see here is one of the features called implicit derivation, and that means in essence that, hey, we can say we can define instances for types that require other types to also have instances, right? So, and that is something that is basically impossible to do without type classes. So if you would try to do this with standard interfaces, with like traits, you would quickly realize, hey, this is impossible, because it can say option extends monoid, but then how do you say that the T has to also have an instance of monoid, right? So this only works if you use something like type classes, and that is one of the powers of type classes. So quickly, like a quick versus thing. With type classes, as I said, we can get like operations on types instead of on specific values. And this really comes in handy when dealing with type classes like monoids, because we can then define things like empty. But there's also dozens of other type classes where this comes in handy. And we can use these type classes, this feature, to derive instances for data types that might hold other data types when they also have instances, right? So we saw an option has a monoid instance when the T inside of that option also has a monoid instance. Okay, does that make sense to everyone, kind of, a bit? Yeah, just like a general idea? Or are they, like, I can do questions right now, like just like something is unclear right now. Questions? No? Okay, cool. So monoids. Monoids are super cool because they are really everywhere. Everything you know might be a monoid. So a function a to b is a monoid only if the b is a monoid, right? So the empty for the function monoid is just returning the constant empty of that b, right? That makes sense. And combining them is just, hey, calling both functions and then combining the results. So we have this a, and then we call the x, which is the first function, and then we combine that with the result of y. So yeah, function is a monoid if b is a monoid. Tuple is a monoid if both are monoids, if both a and b are monoids. So a tuple of a and b is a monoid when a and b are both monoids. And that means that, hey, we can do this very easily. The only thing we do is like return the empties, and then for the empty method, and to combine, we just combine the single values inside. So that makes sense, right? But there's so many more. There's like the either monoid. Either is a monoid when b is a monoid. Map is a monoid when the value of the map is a monoid, when the value type of the map is a monoid. So if you want to like merge two maps, you can use the monoid. Or merge like a list of maps, you can use a monoid, and then it will just look through the keys, and if the key is a match with the other map, then it will combine the values that are at those keys. And future is a monoid if A is a monoid itself. Yes.
Quick question. So
yes.
What do you do if you combine
two maps?
You have like overlapping keys.
Exactly. See, that's a very good question, because map is only a monoid if B is a monoid as well. So you have two overlapping keys, then we'll get the two values, and then use that monoid to combine them, to combine the values. Right, great question. And future is a monoid if the A inside the future is a monoid. So we can have two values that might be there in the future, and then we can just combine them when they're both done using the A monoid. Right? That makes sense. And there's really many, many more. Yes, questions immediately.
Just a comment. I think you mean when A has a monoid.
A has a monoid, yes. There's some, like, all these things are, yeah. Talking about them is really difficult because everyone has slightly different semantics on how to, some people also say like A, yeah, whatever. Yes, good comment, yeah. Jamie?
So these all apply obviously to semigroups as well.
Yes. Well, I'll get there. We'll get to semigroups. Don't spoil it. So monoids are everywhere, and these are just some that are cool. There's many, many more that you will see if you like do a real exploration of something like the CATS library. Right. And so what can we actually do with them, right? We saw this sum function earlier, but there's a lot of other things that are really cool, and we'll see right here. So what I want to do is like create this very simple text text aggregation kind of thing, which is kind of like a real world-ish example. So let's say we have like a text file, and that is this, we parse it into a bunch of lines, and that is this lines file right there on the second line. And then what we do is we map it, we split it into single words and map it using this step function. Right, so this val data has type a tuple of int, and map of string to int, right? And this step function, what it does is it returns a tuple with 3 types, and we do this because a tuple of 3 types will have a monoid if each and every single instance have monoids themselves, right? So 1 is an integer which has a monoid for addition. Word.length is also an integer which has a monoid for addition, and map from word to one, from string to one, from string to int is a monoid because again, integers have a monoid instance. So what this monoid instance will do is if we call the step function on 2 strings, so for example on hello and world, it will for hello, we will turn 1, then the length of hello, which is 5, and then a map from hello to 1. And for world, it will return 1, and then world, which I believe has 6 characters, so 1, 6, and a map from world to 1. And then if we combine these using the resulting monoid of this tuple, we get 2, right? 2, because it's 2 words. So the first parameter is for words. It counts words. The second parameter, word.length, will return the number of characters, right? So we then have 5 plus 6, which is 11. And that will return the total amount of characters. And then we also have a word count, right? Not a word count, but a word occurrence count. So hello, we have a map of hello to 1, and a map of world to 1 because they both occur once. And now if we have a whole text file, we get like we get the number of words in the whole text file. We get the number of characters and a map of the occurrences of each word. So and to do that, all we have to do is define an empty for our type right here, and then all we have to do is just say, hey, just fold this thing and use the empty and the thing that we saw earlier, the combine function. And actually, we can do this even more simply by using the sum function we saw earlier. And in cats, that one is called combine all. And combine all is just fold left with the empty and combine. So we've basically done like a real cool text file analysis in 3 lines of code that are actually like not that hard to understand. So monoids give you like the superpower of aggregation. That's really what they are. Monoids are really, really good at aggregation. And because you have all of these derived instances, you could use things like option and future and whatever. And all of these things, they just magically, it all fits. It's not magic actually, but it all fits together really, really nice. I don't want to use the word magic, I'm sorry. And you can just use this combine all function and then bam, it all works. It's really cool. I really recommend it. So, and what we actually have to think of is that a lot of the cats type classes that come with the library actually have a thing called laws. And laws, I guess the name says it all, are just certain behavior the type class has to have in order for it to be a valid monoid, for example. And the laws for monoid are very, very simple, and almost everything you can think of actually agrees with these laws. So the first one is associativity, and that basically just says that, hey, the order of applying this combine operator doesn't really matter. So it says x plus y and then plus z is the same as x plus y and then z. I actually use z. I usually use z. I'm really, I guess when I'm in London, I accumulate. Okay, so that is associativity. It's very, very simple. And then right identi is even more simple. So we have this empty element on monoids, right? And that basically just says, hey, it has to be actually empty. It has to be a neutral element. So if I combine x with empty, it has to still be x. And then the last law is just the same for the left. So empty combined with x is still x. So these monoid laws, like sometimes people tell me all this laws, it's so confusing, but actually, like, if you break it down to its most simple, and this is like the monoid type, this is basically just how you would expect monoids to behave, how you would expect these types to behave, because associativity is a thing that you would expect. And I will show you exactly why right here. So monoid laws in action. So why do we need these kinds of laws? What are they good for? So what we can do if we write abstract functions like combine all is that we rely on certain behavior of the monoid. So if it does completely nonsensical things, for example, if the empty element isn't actually an empty element, that might result in really weird results. It results in whatever. Yes. So what we can do with these monoid laws is if we have like a bunch of values that we want to combine, this doesn't have to be like just single values. Could be a list as well. And using these monoid laws, we can say, hey, this is equivalent because of associativity. We can start grouping these things individually, right? So what we can say is because if these monoid laws hold for our type, then these two things are completely equivalent, right? And what we can also do is say that, hey, we have this dangling G on the right. We can say, hey, just fill it up with like an empty, and then we have like four different subgroups that we can all combine together. And what some of you might realize right now is that, hey, we had this problem that was very sequential in nature, right? Saying we want to just add all of these things up. We've actually like made them independent of each other. So now we have four independent groups that we could completely computate in parallel, and then we could just sum all of that up in to get the end result. And what monoids allow us is to create a fully parallel version of Fold because of these monoid laws. So this only works if the monoid laws hold. So that's why they're really important. And to do that, I created like a very small example. So we have this list of A's which has a monoid, and to start, we just group them in a specific number for all of our available processors, because we only want to have groups with for the amount of processor, for the amount of CPU cores. And then we can use this parallel map thing, which basically just maps in parallel. And then so from this list of lists, we get a list by folding all of these inner lists in parallel, right? That makes sense, I guess. And then once we've done that, we can just use combine all to get the end result. And now we can, if this list was very large, we can get a huge speed up because we've basically parallelized a lot of that aggregation work. And that is exactly what monoids give us. So I think the laws, that might showcase why these laws are important and why it's cool to have these abstractions with laws that give us certain guarantees. Right, so that was monoids. Any questions up till here? Yes?
So actually, you don't, semigroup would be sufficient for the product, right?
It depends. So semigroup, yes, of course, you're spoiling it again, but but the problem with semigroup is that sometimes you need to to fill up empty values. So if it becomes more complex because you then have to you don't get this empty value to fill up certain things, and then if your list isn't divisible by 3 exactly, then you can't make it fit with empty value. But in essence, it is yes to answer that question. Okay, so any other questions about monoids? No? Cool. So let's talk about this thing called functors. So I'm going to say that functors is actually a lot simpler than monoids. So if monoids were simple to you, this will be even easier. So this is what functor looks like. It might look a bit more scary, but it's actually more simple. So right at the beginning, we might be a bit confused by this thing inside the brackets here, the f bracket underscore bracket. And that is what we call a type constructor, or a higher kinded type. So how many of you are familiar with this kind of syntax? Quite a few. Okay, this is great. So I won't spend that much time on it. So basically what we have is we've defined an abstract type constructor. So this is like a type that takes another type to become a type. And that sounds a bit weird. But if you take, for example, a type like option. Option itself, you can't have values of option. You can only have option of int or option of string. So option itself is not a type, but it's something called a type constructor. It needs another type to become a fully applied type. So option is not a type, it's a type constructor, but option of string is a type. And this f is not a type, but f of a or f of b are types. And yeah, so that's the gist of it. And then the only thing it defines, this functor, is this map function. And the map function, I'm sure you've all seen a million times. It just takes an f of a, and then a function from a to b, and then returns an f of b. So this is the same map that you can see on things like list, option, either vector or future. It's the exact same thing. And of course, all of these things have instances of functor. Yeah, I think that makes sense. So let's talk about this thing called monoidal functors. So we've talked about monoids and functors. Now let's look at what these two properties have in common and how we can like derive a combined abstraction, right? So that combines the best aspects of functors and the best aspect of monoids. So which is basically everything. But yeah, so we have these things that are called monoids, and they're all about this combining two a's and then returning a new a, right? But we could also have things like an f of a and then combining it with another f of a to get an f of a. So this is what we had with our option monoid, right? Where we had two options of whatever, of any type a, where a is a monoid. And then we could get a new option of that a. And that works well, but sometimes we might want to combine, for example, an option of integer with an option of string. And then it doesn't quite fit the structure of the monoid anymore. So something like this. So we have an f of a and an f of b, and I intentionally changed the operator there a bit. And a question for all of you is like, how could we combine these types, and what would be the value inside here where I've had these question marks? Does anyone have a guess?
You can map any of the types to the other type, and you can do the
So a map of a to b, for example.
Yeah.
What's that? Yeah, or the opposite, b to a. Okay, either. Those are all valid guesses, but you can implement them. But the most common one is if you have an option of A, an option of B, when you combine them, you get an option of tuple of A and B, right? So if you have one of both, then you get a tuple. That's usually what you do. You can also do it, as you said, with map and either, and it works for different types. But if you have an option of B and an option of A, usually this is what you want. And that is exactly what the abstraction of monoidal functors give you. So this is what monoidal looks like. So we have this product function. And product is very, very similar to the combined function that we saw in monoid. Right? So it takes an f of a and an f of b and returns an f of tuple a and b. And if you squint a bit, like if you just don't look at the types inside the brackets, it's an f of something and an f of something combined into another f of something, right? Makes sense, kind of? Okay. And then we also have something that is very similar to the empty function in monoid that is called pure, and it takes an a and lifts it into an f of a, right? And we'll see in a bit why this is so similar to a monoid. But this is basically like taking a monoid, lifting it inside the functor. And because it extends functor, it also has, of course, the map function that we saw earlier. So it has three functions: product, pure, and map. Right. And we could define this for an option by saying that, hey, if both of them are true, if both of them are values, right, if both of them are sum, then we get a sum of A and B, otherwise just return none. For pure, we can just wrap an A inside of a sum to get an option of A. And mapping is, of course, just mapping over an option. You can do the same for future. And yeah, exactly. But we can do these for a lot of different things. A lot of different things are monoidals. For example, either and list is also a monoidal. Vectors, there's a ton of monoidals. Yes. Are you going to ask about... I'm going to get there.
Oh, okay, sorry.
You're spoiling all the fun today. Right. So, how many of you have used this function, future.sequence? Almost everyone. Great. That is perfect. Thanks. You're the perfect audience today. That is great. Okay. So, what we want to do here is we want to generalize this. So, we have this thing called monoidal. And right now, this future is very, very specialized, right? It has a list of future of A and turns it into a future of list of A. But it doesn't, like, what are the properties that make it that it only works on future? And we'll see why that is. Or actually, we'll see why that is not the case in cats. So this sequence function takes a list of future of A and turns it into a future of list of A. So it takes, like, two type constructors and turns them inside out, right? So a list of future to a future of list of something. And here do we define a general version? And oh my god, this looks crazy, right? So this is like, what is this? We'll try to break it down step by step. So first up, we instead of using future, we use this abstract f, this f-type constructor, and we say, hey, it has to have a monoidal instance, right? It has to be monoidal in nature. It has to be a monoidal functor. And then we see here we take in a list of f of A, and we return an f of list of A, right? So that part is not that scary, right? I hope. So what do we do here? So we fold over this thing, and because we want to return an f of list of A, the seed of our fold, the empty value, has to be an f of list of A. And to do that, the thing that we do is we take the empty value of list and then use the pure function to go from list of A to f of list of A, right? So that's the first step. And then we have to define the accumulation function. And that, because everything inside of that L, inside of a list of f of A, is an f of A, that is going to be our current values. So this f of A is all of the values that come out of the fold. And this is the accumulator, right? The f of list of A that we, in the end, want to accumulate all the values to. So the first thing we do is say, hey, let's use this product function to combine these two f values, right? So we have an f of A and an f of list of A. And if we use this product function from monoidal, we get an f of tuple of A and list of A. And what we can then do is use the map function to go back to an f of list of A, right? So we have this side here is the A, and this is the list of A. And to combine them, we use this plus double colon, which is defined on list, and it just appends, it prepends the A to the list. So what we get right here is actually just saying, hey, we're going to combine them and then add the A to the list, right? And of course, this might be a bit tricky, but actually, if we look at how the combine all function in cats was defined, for monoids was defined, this is actually very similar. Like inside of the seed, we use. I'll get to you. Inside of the seed, we use this pure function, where in the monoid combine all, we used empty. And inside the aggregation, we use this product, where with monoids, we use the combine function. So this is actually very, very similar. It just uses the fact that these are not just monoids, but also like higher-kinded monoidal functor things. And it might be a bit clearer if we look at something like this. So these are actually completely equivalent, these two things. So map n is just a basic like syntactic sugar that says that, hey, if we're going to use product and then map, we can use this map end function, and that is also defined in cats. And what it means is that basically, hey, we have an f of a and an f of b, and then we can map both of those type with a function f that takes an a and a b and returns some other type c. Right? So right here, we have an a and a list of a, and then we use this function to go from a and list of a back to list of a. And that is basically all it is. So this is the sequence function, completely generalized, and I will take your question.
Yeah, so you're using the list at a concrete time.
Yes.
You could potentially generalize it even more by using a monoid, right?
You could definitely do that, and of course, we will do that. But thank you for the question. That's a great question. Yes. Are there any other questions regarding this? Because I think, like, looking at this, it looks like when I first looked at this, I was like, what in the God? But actually, like, it's not that complicated. I think it's not that complicated. I've done this a bunch of times. I think, like, if you break it down, it starts to make sense, right? Does this make sense? Like, raise your hand if this makes some kind of sense. Okay, yeah. So to those that where it doesn't make any sense, can you like maybe like a question or something? Yes.
Do you have to be fold right? Or
That is actually a very good question. So you could do the same with fold left. Fold right is just the lazy version, so it doesn't stack overflow if you, for example, use a stream or something. But yeah, it's kind of. I just used the cat simple. I could have used fold left for this example as well. Okay, other questions? Okay, so I'm going to move on. So we've seen future.sequence, but there's also future.traverse. And this might be look a bit more tricky, but it's actually very, very similar. So we have, this is the traverse function inside future. We have a list of A, and we have a function from A to future B, and we use that to go to future of list of B. But actually, if we were to first map using this f function, right, we get a list of future of B, and then we return a future of list of B. So actually, like, sequence is just map, traverse is just map and then sequence. So that is the whole secret to traverse. So and actually, like the implementation is super similar, right? So, but instead of having an f of a here, we only have an a, and then we use this f function to go to f of b, and then we can use the map n. So it's very, very similar. We just have to apply this function here, and yeah, that's all it is. So traverse is the same as calling map and then sequence, and it's kind of like how you have flat map and flatten, right? So flat map is the same as map and then flatten, right? And that is exactly what this is. Traverse is just map and then sequence. And you see this kind of pattern where you first map over something and then use something else a lot in this abstract kind of code. But it's, yeah, I think like flat map is the best analog. So traverse is what you're going to use if you want to map over something and then sequence it. Okay. So, and actually the cool thing about this is that the laws remain the same. Like the laws for monoidal functors are the same as for monoids. So if you use the product instead of combine, it has to still be the same. Right identity, left identity, you'll figure it out. It's really not that difficult. So, and of course I have to tell you like a tiny secret. I've kind of been lying to you a bit. So what we call monoidal is actually usually called an applicative. So you might have heard of applicative and not monoidal. And applicative is what we call these monoidal functors in programmer circles. So mathematicians actually prefer monoidal, but non-mathematicians like the Haskell programmers or whatever, they thought that applicative is a better name for this thing. So I think monoidal is cooler because it basically says that, hey, this is like a monoid but in a functor. But because I don't want to confuse you when you like go into the internet, so like, oh, this is cool, what's this monoidal thing, and then you don't find anything, I'm just going to be using applicative from now on. So whenever I say applicative, just think back to monoidal. And I'm sorry to have to do this, but I wanted to like make a good transition. I hope it worked somewhat. So next, we're going to answer the guy in the back's question, where we said, hey, right up till now, we only used list. So what's the thing about that? What about vector, stream, whatever? There is this type class called foldable in cats. And it has one abstract method and one that is combine all that we saw earlier. And combine all is just the generalization of the thing that we used list for. So we have an abstract f again, a type constructor, and then combine all just says that, hey, if I have an f of an m, which is a monoid, I can produce a single m. And actually that is a derived function. So the more general function is FoldMap, and that says that if I have an f of a where a can be anything, and I give it a function that turns an a into any monoid m, I can then use it to produce a single m by aggregating all the things. And of course, again, FoldMap is just equivalent to map and then combine all, right? So if you map over list and then use combine all, that is the same as just calling FoldMap using the function f inside here. Does that make sense? Yeah? Questions so far? Cool. Oh, yeah?
Using the identity.
Right. So because, yeah, that's a great question. So combine all uses FoldMap, but because m is already a monoid, we can just use identity, which is going to return an m, and then it will just combine it inside of that. Right? So with FoldMap, you map this f of a to an f of m, and then aggregate it. With combine all, it is already an f of m, right? And so you can use this FoldMap because you only need to define one of these. You don't need to define both.
We just need to add the extra m to f
I'm not sure what you mean, but yeah.
Combine all equals FoldMap fa and identity. That's the parameters.
You are completely right. I forgot that. Yes. Sorry. Yes. Yeah, exactly. So I would have to, yeah, of course. The FA, I didn't pass it, and that is a stupid mistake. Yeah, good thinking. Good. Okay, so we can define this for list, for vector, but also for things like option and either, because they're also foldable. They just have like a single element or a 0, right? So option is kind of like a list with either 0 elements or 1. So it works for them as well. So we can use all of these things with a lot of different types, and that makes it even more general. So now we've abstracted over monoids, and now we've also abstracted over the containers that we want to aggregate. So this gives us even more power and even more, because it works with even more things, and that's really cool, in my opinion. And now we come to the main topic of my talk, and that is the traverse type class. And it's yeah, I'm sorry, it takes a bit long, but yeah. This is exactly what I'm here for, and it's just, you talked about, hey, we used list all the time, but let's just abstract over that. And it's actually like, it's fairly simple. So traverse extends foldable and also functor for some reasons. And it only has these two methods, traverse and sequence. And we can define one in terms of the other because we have map from functor. And so it doesn't really matter which one you implement. You can get one from the other because map and then sequence is equal to traverse. So we can do this. Wait, before I do that, let's just go over the type signature real quickly. Before we had a list of f of a to an f of list of a, but now we just said, hey, why list? Let's just do it for any kind of t, right? And so it works for any kind of t with this type class. So we have a t of f of a, which could be, for example, a list of future, and turn it into a future of list with the sequence function, or the same with traverse. But it could be anything, and that is like the real power of this traverse type class, is that we've not just abstracted over the applicative, but also over the container, just as we did with FoldMap and monoids. We'd say that, hey, we can do this for any pair of traverse and foldable, traverse and applicative, and traverse or monoidal. And that means that we can turn a list of future into a future of list. We can turn a list of option into an option of list, but we could also turn an option of list back into a list of option. We could turn a list of either into an either of list. I could go on forever because there's so many things, and if you don't use these kind of abstractions, usually what you end up doing is you need these functions, but you don't realize you need them, and then you just hand code them, hard code them somewhere, and you don't even realize that there is this generalization that it encompasses all of these very, very useful use cases. And yeah, we can do this for vector option, but also for things like either, where the left type is like a fixed type. So, and we use a type alias here, but what we usually do is this with this thing called kind projector, which says that, hey, this works for any E, and it's a traverse for either, where, of course, either usually takes true type parameters, and this little question mark thingy says that, hey, this is basically a whole. So either of E and question mark is a type constructor that needs a single type to become a type again, right? There's no other way to use this in Scala, right? So option takes a single type parameter, vector takes a single type parameter, either takes two, and the same goes for map. Map is also a traversable for the key. Maybe I should use that example. Yes?
Why do you call it either string then?
That is a very good question because I'm dumb and I forgot to change it. Yes. Man, you guys are really good at noticing my mistakes. Okay, so yeah, some of the things I talked about, like what we can do with this traverse type class, go from list of future to future of list. And what's cool about this, I think, is that because this type is so general, we can usually see what this function does just by looking at its signature. So a list of futures to a future of list, what would that do? Like, anyone have a guess? Exactly. That's the only reasonable thing it could do, right? And that's exactly what it does. And a stream of option to an option of stream just says, hey, if any of these are none, I'm just going to return a none. Otherwise, I'm going to return all of the stream values in A. But there's also either E of IO of A. We can turn that into an IO of either E and A. And there's also this cool thing where you could turn a vector of validated NEL of error in A into a validated NEL of error and vector in A. And I think that's like one of the coolest things. But what is validated NEL? That is some weird shit, man. So, okay, I'm going to explain what it is because actually, again, it's pretty simple. So it's like a seal trait. It's this ADT thing. It has two type parameters, kind of like either. It has either an E, which kind of maybe invokes like error, and an A, which is just a simple value. So it has the first case is valid, which just wraps a single A. Then we also have a case invalid that wraps a single E. And that is all that validated is. And validated NEL is just validated where the left side is wrapped into a non-empty list. Yeah, so validated NEL is just this very simple thing. And now you might ask, why would we do this? This is basically just like either. But it has some really neat properties. And that is that it accumulates errors because it doesn't have, in its applicative instance. That means that if we combine two validated NELs, it will then combine if both are errors, it will combine the errors using a monoid. Actually a semigroup, but yeah. Combine using the combined function of a monoid, right? So if we have two validated NELs of error and users, and they're both false, they both contain a non-empty list of errors, then if we combine them using mapn or a product or any of the functions from the applicative or monoidal type class, then it will accumulate all of these errors inside of this non-empty list. So let's say we have this validate function which takes some kind of string and wants to parse it into a user, which can be some user class. And by doing so, of course, not any string is going to be able to be turned into a user. So we turn this validated NEL instead, which might have either a non-empty list of errors that might have occurred by parsing this string, or it will return a single user that is completely valid and okay. Right? And then what we can do with this is that say, hey, we have, again, like a text file where every line represents like a user that will have to be parsed. So we have a list of string, for example. And then using traverse, we can turn this thing into a validated NEL of error and list of user. And that means that either this type here, users, is either a non-empty list of errors or it's a list of valid users. And that works precisely because traverse, again, flips this thing inside out. So it will run this validate function for every string in this lines variable, and then it will validate them all and see, hey, you either have a bunch of errors or you have a valid list of users. And this is how you do very simple, very clean functional validation, and it works really, really nicely, in my opinion. Yeah. So questions about that? Sorry? Right. So if there are a bunch of errors, it will return all of them, right? So validated NEL is a validated of non-empty list, right? So it's actually this thing is a validated of non-empty list of error and list of user. So it will accumulate all of these errors inside of the non-empty list. So I prepared this thing that if you're okay, question.
This is essentially an either, right?
This is exactly. It's essentially an either. But if you use the applicative of either, it won't do error accumulation. And that's because the applicative of either doesn't require this E type to have a monoid or a semigroup.
But you can't have both a list of errors and a list of users.
No, exactly. So it's a disjunction basically. It's either this or that. But yeah, exactly. Okay. It is what we call isomorphic. It has the same structure as either. But it has a different applicative instance because it requires a way to accumulate these errors on the left-hand side, if there is. Okay. So if you're still not convinced about traverse, I have a bunch of arguments, and they boil down to I'm somewhat active on Stack Overflow, so maybe once or twice a week I will look into Stack Overflow, answer a bunch of questions. So, and usually the kind of questions I see are basically all solvable with like 2 or 3 lines of traverse. And I just looked at like the last 6 months of my Stack Overflow history of my answers, and I just took all of them and copy and pasted them here. So, hey, how do I turn this list of either t of future to either t of future of whatever? Well, that's just, hey, we turn this thing inside out, right? So it's a list of something, and then we have a something of a list. Hey, okay, that's easy. It's just traverse. So we have this list of IOs, and we want to turn it into an IO of list. Hey, that's traverse. We have an error, either error option, either something, I don't know, but it's just traverse. We have a list of Kleisli to a Kleisli list. It's traverse. How do you combine sequence of validated NEL? Sequence of validated non-empty list into validated of non-empty list sequence. That's exactly what we did just now. That is just sequence. That is just traverse. How do I do this? Oh my God, I have this thing and I have this other thing and I want to combine them and I don't know how to do it, blah, blah, blah. It's just traverse. That's the answer. It's like, yeah, this is just, yeah. The answer is traverse. Like, if you start using it, you realize, oh, I have this bunch of code. It's just traverse. Why am I doing this? And okay, and that is my main argument for traverse. And I don't know if do we still have time?
You guys can probably grab questions around the pizza.
Okay. Okay, I'm just gonna have like 1 or 2 more slides. So we have this thing called semigroup, and it's like a monoid without empty. So it's just like a associative combined thing. And then monoid, of course, extends semigroup, and that's the whole thing. Semigroup is just the thing without empty. And then it's nice because like sometimes you have empty lists and you want to reduce them, and then reduce with throws like a runtime exception, which you never want. Runtime exceptions are bad. And so you have this non-empty list, which is not a monoid because it doesn't have an empty element, because of course it's non-empty, and it's instead it's a semigroup, blah, blah, blah. Bunch of cool things. You can do max safe because max is unsafe because it might throw And yeah, that works. Semi-groupable functors are like monoidal functors or like applicative functors without the pure. And that's it. So what can we use it for? We can define it for a map, for example, because you can't define pure for map, because how do you lift a pure value of v into a map of key to values? We always need a pair. That's why we can't have an applicative. What we can instead do is have this thing called apply, which is the semi-groupable version of applicative. It doesn't have the pure. That works. Okay, conclusion, blah, blah, blah. We learned about monoids functors, monoidal applicative functors, and foldables, and of course, non-empty lists, and validated, and the almighty power of traverse. And I hope this was like maybe some of you will take a look at cats, because I think it will make a lot of your lives actually a lot better. Yeah, thank you so much for listening. You can find me on Twitter, GitHub,